Okay, let us proceed example 5.6, which is tank flow rate. So water flows from a large tank through a large pipe that spills into two smaller pipes as shown figure below. If viscous effects are negligible, determine the flow rate of the tank and the pressure at point 1. Now let us see. So you have, I think, it is clear that if you have tanker, then water will flow out with high velocity. So I think once you have the volume flow rate, then you can calculate other parameters like velocity, pressure, etc. So this is level of water at 0 point. Point 1 is here, then point 3 is this one, and point 3 is this one. So let us see. You have 7 meter head, total height of water up to reservoir level, and the tanker is 3 meter height, and the diameter of pipe 2 is 0.03 meter, and pipe 3 0.02, and pipe 1 this one. Now let us see the solution. So applying Bernoulli's equation again between water surface and point 2, then you have total head in reservoir at point 0, and then you have pressure head, velocity head, then total potential head. So P naught is 0 because it is open to the atmosphere. Here P naught is 0, then P2 is also 0 because it will flow out to the atmosphere. Here at this point it will be 0. Then V naught initially at rest. Water is at rest, then Z naught 7 meter because you have total height 7 meter, and Z2 is 4 meter. Z2 is 4 meter, this one. The height of this is 4 meter because 7 meter subtract 3 meter, you can find the height of this above this level. So let us solve now. So you can solve the velocity which is going out through pipe 2 to G Z0 minus Z2. So 7.67 meter per second. Similarly, you can apply Bernoulli's equation between water surface and pipe 3. The same Z0 and P0 over gamma 0, and initial velocity is 0 because it is at rest. Then you can find the velocity which is going out from this one. So we have calculated V2 velocity coming out from this pipe and velocity at point 3 coming out. So once you compute velocity, you can apply again according to continuity equation. Total discharge Q, which is coming in pipe 1, will be equal to the sum of Q2 plus Q3. So discharge is area times velocity. So area of the pipe is pi over 4 d2 square times v2 plus pi over 4 d3 square times v3. Since we know the velocity already from the above equation, then you can calculate 9.10 times 10 to the power of negative 3 meters per second. Then once you have total discharge, then you can calculate other parameters in pipe 1. But let us calculate pressure in 1. Applying Bernoulli's equation between water surface and point 1, the same total head in reservoir equal to total head in 1. So since Z1 is 0, Z1 is 0 means Z1 is 0, this one. So just the datum is this one, reference line. So no head above this. So Z1 is 0. Then V1 you can compute now. Total discharge you have already Q over A1 4.63. This is the velocity which is coming out from pipe 1, which is this one. This is pipe 1. Then it will bifurcate to two pipes, pipe 2 and pipe 3. So you can have velocity here. So once you compute velocity, then you can calculate pressure at this point. So pressure at this point will be calculated as using Bernoulli's equation between water surface and point 1. then P1 will be like this. So you will get the 5.79 times 10 to the power 4 Newton per meter square. Then you can make 10 to the power 3 into kilo. Then it's 7.9 kilopascal or kilonewton per meter square. So this is tank flow rate. And this is given as exercise for you. You have closed tank. Then you have just a closed tank having 8 meter height, contains water with air above it. So air is here. It is closed. The height is 8 meters. The air is maintained at a pressure of 10.5 meter of water. So the air pressure is 10.5 meter, which means this is head, which means P over rho G. P over rho G is this one, and 5 meter below water surface. So 5 meter below water surface here you have, then diameter 250 millimeter pipe having a length of 25 meter. So this is 25 meter length given, conveys discharge, some discharge you will convey. Then what will be the flow rate of the nozzle? So at this nozzle, what will be the flow rate? So diameter is 100 millimeter, but initially you have 250 millimeter. So please do this as exercise. Then if you have any question, you are welcome. Okay, so let's go to example 5.7, horizontal and vertical venturimeter. So I hope in the previous discussion we have seen pressure and also practical application of Bernoulli equation. I think we can measure the flow rate coming out through some pipes. So you have venturimeter, P-pot tube, and also other things like flow through reservoir or orifice, etc. We will continue. So let us see. This is horizontal. Water flows through a horizontal venturimeter, 15 centimeter by 7.5 centimeter. 15 centimeter is the inlet diameter, and 7.5 centimeter is the throat diameter, D2. So if the gauge pressure at the inlet is this one, 58.67 kilopascal, and the absolute pressure at the throat must not fall below this one. So it should be more than. So this is the absolute pressure at the throat. This is throat, this is inlet, then convergent part, then divergent part. Then it will go out to this as original dimension. So determine the maximum discharge which can pass through the venturimeter. Take atmospheric pressure 101.43 kilonewton per meter square, and coefficient of discharge CD is 0.96. So solution is very simple. I hope in the previous session in chapter 3 we have seen absolute pressure is atmospheric pressure plus gauge pressure. So you have to add atmospheric pressure. So total absolute pressure is given this one. So absolute pressure head, again you can compute P over rho G, which is gamma. So you have 70.3 meter of water. So let us go to at inlet and throat. So at inlet, absolute pressure head already given. At inlet to the venturimeter, you have already given 25.53. So this is just given 25.53 over 9.81. So 2.5 meter of water. So at the throat, which is the throat, so you have A1, this one, then A2, this one. So I think next to this, let us see now the maximum discharge is given by this equation. Actual discharge is given by coefficient of discharge times theoretical discharge. So theoretical discharge is nothing, continuity equation, you know this, A1 times V1, theoretical. So according to the venturimeter equation, you have inlet, then throat, then you will get this equation, general equation of actual discharge. So you have A1, area 1 at the inlet, area 2 at the throat, then divided by square root of A1 square minus A2 square, then square root of 2G times pressure difference H, P1 minus P2 over rho G. So after substitution, you get actual discharge will be this one. So this is horizontal venturimeter. So you can try this as exercise. If it is horizontal, you simply substitute in this equation. So I think coefficient of discharge in this problem is given 0.98. So the answer should be 0.165 meter cube per second. So this is left as exercise for all students. Please try. Then example 5.8 is just venturimeter with differential manometer. So when any fluid is going out this one, then some displacement you can just see. So let us see. A venturimeter is placed in a vertical line to measure the rate of flow of benzene with specific gravity 0.899. The inlet diameter of the venturimeter is 20 centimeter and the stroke diameter is 8.75 centimeter. Benzene mercury differential manometer is used to measure the difference in pressure between inlet and the throat of the meter. So when the gauge reading X is 10 centimeter, what will be the gauge reading in centimeter of benzene? The discharge passing through the meter, the throat velocity. So take coefficient of discharge 0.99 and specific gravity of mercury is 13.55. So I think when just the fluid is going through this venturimeter, then you will have some displacement X. So this displacement X mass density of manometer liquid, you have X 10 centimeter. So what will be this result? Let us see. Solution is clear. So the differential pressure here is evaluated from manometry from this equation. H is difference in pressure divided by gamma, then equal to X times specific gravity of the manometer fluid divided by S minus 1. This is S of the liquid. So benzene specific gravity is given. So you substitute here, then you will find 1.405 meter of benzene. So this is just the H of benzene. What will be the gauge reading in centimeter of benzene? So gauge reading you can read. So you have this venturimeter with differential manometer. So what will be actual discharge? Coefficient of discharge times A1 divided by A1 over A2 the whole square minus 1 under square root times 2GH. So this is the equation for the venturimeter with differential manometer. So you simply substitute the equation. So you have coefficient of discharge given, then you will find 0.032 meter cube per second. So this is the discharge flowing out through the venturimeter. If you have some fluid which is going through the venturimeter and also mercury is used as differential manometer, then displacement X you have, then you have this discharge. Then velocity from continuity equation, discharge divided by area. So if you substitute, you will find the velocity which is going out. So this venturimeter, the throat velocity. This is the throat. Throat is just very narrow portion of the venturimeter. This is the inlet, this is outlet. So flow direction is going through this one. So we read X distance just D2 mass density of manometer liquid. So if it's the gauge field with liquid in pipe of mass density rho you have, then you can apply. So this is piezometer rings. You can just adjust according to the flow. So as exercise, please try this one. Horizontal venturimeter with inlet and throat diameter given respectively is used to measure the flow of water. So water is flowing out. So reading of the differential manometer connected to the inlet and the throat is 20 centimeter of mercury. So if the coefficient of discharge is 0.98, so determine the rate of flow of water coming out from the venturimeter. So just we are using differential manometer, mercury, this X distance, then what will happen? So please try this one as exercise.
Okay, so this is all about today's tutorial. Hopefully you liked the video. And thanks for watching.